Thanks everyone for making it to the end of the day. And we're in the section of the students that are part of who received a TCCP scholarship from the center here. Our first speaker is Nofar Schottlender. I hope I pronounced your name correctly. From Asheri's lab, and you're welcome to come in.
Okay, so hi everyone, I'm Nofar, I'm a PhD student at Asheri's lab, and I'll be talking today about understanding the effect of hyperbaric oxygen therapy on an Alzheimer's disease mouse model. So dementia is characterized by decline in memory and language and other thinking skills that affect a person's ability to perform everyday activity. It is an umbrella term for many diseases that directly and indirectly damage the brain. And the major issue with dementia is that is underdiagnosed. When there is a diagnosis, the pathophysiology is already spread through the brain. It is very hard to treat. So currently, there are more than 55 million people who live with dementia worldwide, and every year there are approximately 10 new million cases. It is a major cause of disability and dependency among older people, and the cost both financially and for caregivers is enormous. So Alzheimer's disease is the major cause for dementia. It is characterized by the accumulation of A-beta plaques and neurofibrillary tangles. The amyloid cascade theory says that the accumulation of A-beta is the initiating factor that causes this disease, which is why I work with the 5X FAD mouse model, which is a transgenic mouse model that expresses 5 mutations under a neuronal specific promoter, which causes these mice to accumulate A-beta and also experience astrogliosis and microgliosis. So hyperbaric oxygen therapy, or HBOT, is the treatment of 100% oxygen under a pressure that is greater than 1. It has been in use since 1662. But back then, people didn't know what it does. Today, we know that hemoglobin is saturated by 97% at sea levels, but there is a small fraction of oxygen that is dissolved in the blood. And as we increase pressure, we increase this fraction of oxygen, which can reach everywhere. So HBOT promotes angiogenesis, it reduces pro-inflammation, and it improves cognitive decline. And I wanted to measure what it does to the mitochondria. So what I do, I take 5X and wild-type mice. I give them a cognitive test, and then I treat them for 1 hour daily at 2 atmosphere absolute for 1 month. And I also take a control group, which I put also into the chamber, but I don't raise the pressure. Afterwards, I give them more cognitive tests, and then I take their brains for bioassays. So the nest building test, it is a test for quality of life and self-care, which we know that in Alzheimer's disease is damaged. I give the mice materials to build the nest. So think about the best environment that you would like for yourself. So for a mouse, it's a lavish, big nest. And we can see that in the 5X mice group, they perform significantly worse than their counterparts, wild-type, and the 5X treated mice, which perform significantly better and take care of themselves after the treatment, both in their score and in the nest height. So object recognition is a test for long-term memory. I show the mice 2 identical objects, and 24 hours later, I show them the old object and a novel object. And I test for how long they spent with the novel object. And we can see that the 5X untreated group spent approximately 50% of their time with the novel object, so they didn't discriminate between the objects. For them, it's 50-50. These were the same. But the 5X treated group did significantly better. And in a short-term memory test, or the Y maze, I give the mice time to explore the maze when one arm is closed. I take them out for 2 minutes, and then I give them time to explore the whole maze, and I check for how long they spent in the novel arm, and we see the same result. The 5X untreated group do not perform as well as the wild types, but after the treatment, they do. When we look at the accumulation of A beta in the hippocampus, in the CA1, we see a reduction in the A beta load, in the dentate gyrus of the hippocampus, and in the subiculum of the parahippocampal region. So in order to understand these phenomena, I went to study the mitochondria. Since the mitochondria consume roughly 90% of the oxygen that we breathe, and they do so in the oxidative phosphorylation process, which is the process I focused on. So these mice experience alterations in their mitochondria. They experience reduced ATP levels. They have excessive fission. They show downregulation of their mitochondrial transport, and they have reduced basal respiration. So what happens when we go into the oxidative phosphorylation process and check for complex 1 and complex 2 mediated respiration? And I do that by giving complex 1 its substrate, or NADH. I later on block complex 1 to get the background respiration, and then I give complex 2 its substrate, succinate, and then I block complex 3 to get the background respiration. And what I see is nothing. I don't have any differences between the groups in complex 1 or complex 2 mediated respiration. But I wasn't discouraged. I thought, okay, maybe I'll go check for complex 4 activity, since complex 4 is the complex that binds oxygen, and maybe I'll see differences there. I do that by blocking everything and isolating complex 4 and giving it its synthetic substrate, which is TMPD, and then I block complex 4 by using sodium azide. And again, I get no differences. So these results, which I've shown you in mitochondrial respiration, were actually in males. But when you go to the literature, you see that females actually have a reduced respiratory capacity as early as 2 months rather than 6 months in males. They have less subunits in complex 1 and complex 2. They have more metabolic pathways which are altered. And in another AD mouse model, they show their reduction in maximum respiration. So when I go and check for mitochondrial respiration in females, again with NADH and succinate, I do see differences. I see that the 5X untreated group have a significantly less oxygen consumption rates, and after the treatment, this is improved, and this is accompanied by reduction in the levels of complex 1, perhaps because complex 1 has become more effective due to more oxygen. Complex 2 shows the same result. The untreated group show a reduction in the oxygen consumption rate, but an elevation after the treatment. This, their levels is not significant. And when I go and check for complex 4 activity, I see the same result. The untreated 5X mice have a reduced oxygen consumption rates and an elevated consumption rates after the treatment, and no significant result in their levels. So not all are roses and hugs with mitochondria. We do need them. They're very important. They produce ATP, but they are the major source of reactive oxygen species in the cell. And we are talking about a model that increases the diffused oxygen in the blood. And on top of that, the 5X in 80 mice and 80 patients show an elevated levels of oxidative stress. So I wanted to measure what happens to these mice in regards to oxidative stress. And what we found is that the 5X mice indeed do have higher levels of oxidative stress on their DNA and on lipids, but after the treatment, they have a reduced oxidative damage. And this is probably due to an elevation in the antioxidant enzymatic activity. This is SOD activity and catalase activity. And so this is probably the reason why they have a reduced oxidative damage after the treatment. So to conclude, we saw that HBOT improves 80 mice performance in quality of life and memory-like behaviors. HBOT reduces plaque load. We saw that they have alterations in their oxidative phosphorylation process, but HBOT improves mitochondrial respiration only in females. And that this treatment induces antioxidant enzymatic activity, thus reducing the oxidative stress in this mice. So by this, I would like to thank the organizers for this great conference. I would like to thank Uri, my PI, who I would not be here without him, and you for listening. Thank you.
Questions? I have a perhaps naive question about why is there actually a difference in respiratory, mitochondrial respiratory between males and females?
So first of all, this is a more dominant female disease in the population. But also, I'm currently trying to figure out how to better characterize each cell subtype, because we know from the literature that, for example, astrocytes have a more tendency to glycolysis. So it might mask the effect because I take everything.
Right.
So I'm trying to figure out how to do.
It's like single cell or something.
Yeah.
Tricky.
Yeah.
Any more questions? Otherwise, we'll move. We'll thank Nofar again.
Thank you very much.